Visibot is a spreadsheet for real-time dynamic control of robots. That's a combination that hasn't really been tried before. Like in a regular spreadsheet, each cell has a name and a formula, and the formulas don't have to be in any order. This system figures out dependencies and calculates them in the right order. Unlike a regular spreadsheet, cells have not just a single value, but a time series of values. You can see a graph of the value over time, and you can scrub back and forth. This is the robot it's controlling. It's a biped about human size. Here's what the spreadsheet makes it do. It fires up the robot. It was swinging from a previous fall over. Taps the toes a couple of times, sets it down, and it's balancing on its feet. So all the code to make it do that is here in the spreadsheet. So let's look at it. We'll start with that some cells are sensor inputs. This sensor input is from the gyroscope on the torso. So that gets the formula is just a default value, but when the robot's running, it plugs in real values. From that, we can calculate with some 3D math. Starting from the torso position, we do a translation and add a rotation. We keep doing that all the way down the line until we've got the positions of the feet. So far, we've just been, and we can render those into a CAD model. We take each of those positions we calculate and load an STL model off disk to render it. Well, so far we've just been processing sensor values, but now we can use those positions to control the robot. So this is the position of the right ankle relative to an inertial reference frame around the torso of the robot. And we have a target position for those, so we can calculate an error. And then we can do a little bit of high pass and low pass and clamping, filtering on that error to get a balanced feedback term. And then we can take those balanced feedback terms and calculate an ankle torque. The ankle first goes through a phase of tapping its toes, but then it switches into balance mode when the robot's on the ground. So we've been looking at a run from a few minutes ago, but the exciting thing is to run it live on the robot. So if I hit Command L, it will fire up the robot, upload the spreadsheet to the robot, run it in real time. It's recalculating every about 100 times a second and streaming the results back so I can see numbers change. And if I were to change something, it has immediate effect on the robot. So let's go. I lost it. Let's go to the. Oh yeah, here we go. Here the balance feedback terms that we looked at earlier. So if I change one of these numbers, maybe like this, it will probably fall over. Yeah, it looks like it fell over. We weren't looking at the video while that happened, but we can go back and see it. It has to load the video. I should mention the robot's in my lab in Silicon Valley, but I'm currently in England. So I'm doing all this over the internet. So we can go back and watch a replay of the whole episode. Wakes up, taps its toes, is lowered down to the ground, starts balancing, ropes go slack. And then a few seconds later, I started messing with those parameters. So let's scroll forward till that point. And forward in real time again. So it falls forward. There it goes. So we could look at if we want to understand further what went wrong, we can look at all the values the spreadsheet calculated while it was doing that. So this language has numbers, vectors, matrices, 3D graphical objects, and I should mention that it has the behavior trees, which are a convenient way of kind of running through a state machine. So that's the complete code. Zoom out to see the whole thing. It's big, but not giant. So the goal is for this spreadsheet to be a productive way of getting robots to do what you want them to do. The edit run feedback cycle is a lot shorter than if you were editing C++ code and recompiling and running it. You can change numeric parameters more or less instantly on the robot, and if you change code, it only takes a few seconds to rerun it. Adding ad hoc visualizations is also easy. So before I mentioned that it's calculating, it has a balance error and it's calculating a balanced feedback term, and that's where it applies some low-pass filtering. So we can compare the input and output of that low-pass filtering. If I just say ad hoc 1 equals line plot balance.air times 0, 1, 0 to extract the y component, and balance.yfb. It'll show a phase plot of the balance input and output. If there were no filtering, that would be just a straight line, but there's some filtering, and here we can see it clamping the value. With a little more work, you can combine plots. This shows everything about a joint, the pneumatic servo valve, torque, position range, torque range. And so it's easy to sort of see exactly what that particular joint was doing at a time when something interesting happened. So that was a demo of controlling a dynamically balancing robot in real time from a spreadsheet. Advantages are the spreadsheet automatically shows us graphs of everything it calculates live, and we can go back later to look more closely at something. Any of the parameters can be adjusted by dragging the mouse over them, and we can see the behavior change live. The spreadsheet can include visualizations of robot movement, such as rendering the position the robot believes it's in from a CAD model, which you can compare to the video. Or you can add quick XY plots to see how two cells behave relative to each other. And we can do it all remotely. You can find more information and demos at visibot.com. There's now a version that runs in your browser, including a simulated robot, so you can do all the things we did here without any hardware. I only have this robot standing so far, but the simulated robot has a demo of it walking. Like and subscribe.